Welcome to Truths, the podcast where love for Torah, Israel, the Jewish people, and God meets fearless critical inquiry. Through powerful conversations and thought-provoking solo teachings, we explore how timeless Jewish wisdom can ignite 21st century meaning, drive personal transformation, deepen our connection to God and to one another, and inspire bold action to heal our world. Here's your host, Rabbi Dr. Levi Brackman.
Welcome back to Truths, Jewish Wisdom for Today. Thank you so much for joining. I'm your host, Levi Brackman. Before I begin, if you like this podcast, please subscribe, like it, leave a review wherever you listen to the podcast. That helps with the algorithm and also helps other people find this content. Thank you so much. Now, today's conversation is a real treat because we get to live at the intersection of cutting-edge physics and the inner life of faith. I was joined by my friend, Professor Hagai Diamandi, who is now an assistant professor in applied physics at the Hebrew University of Jerusalem's Institute of Applied Physics. Formerly, he was a postdoctoral researcher in Professor Peter Rakich's lab at Yale University. During his postdoctoral research, Hagai and his family were part of our New Haven Jewish community for about 3 years. And as he prepared to head back to Israel to open up his new lab, we sat down to talk about what he's learned scientifically and spiritually. We started our conversation talking about his work and his research, and how ordinary optical fiber, the same kind that carries the internet, can become a distributed sensor, sensitive enough to detect tiny disturbances far away, and even, in principle, to pick up vibrations from speech. From there, we moved on to talk about optomechanics, the science of how light and mechanical vibrations interact, and how resonators can trap standing waves of light and sound, amplify those interactions. Then we went on to talk about things that are genuinely mind-bending in physics, how to cool those systems towards the quantum regime, the measurement problem, and what it means to know something in a world where observing can change what's observed. Along the way, we talk candidly about the tension people feel between physics and metaphysics, between science and religion, between spirituality and physics, and why some scientists prefer not to mix the realms. We also spoke about why Hagai himself experiences faith less as an argument from scientific gaps of knowledge and more as a way of living with mystery, uncertainty, and humility. So if you've ever wondered whether modern physics makes the world feel less enchanted or more enchanted, or you're generally wondering or interested in the intersection between physics, science, religion, and spirituality, then I think that you'll love this one. Let's get right into it. Thank you, Hagai, for coming on to the Truths, Jewish Wisdom for Today podcast.
Thank you for having me.
And you have now lived here in New Haven for 3 years and got to know you when you first moved here. And for the audience, just tell us a little bit about what brought you to New Haven.
Okay, so as you said, my name is Hagai Diamandi. I'm originally from Israel, and I carried my PhD in Bar-Ilan University in electrical engineering. And moving forward on the academic journey, I had to spend a few years abroad in a postdoc. Usually in Israel, it's mandatory to have a few years of good postdoc in one of the elite universities abroad. So I found my way here to Yale, working in the lab of Professor Peter Rakich at the Department of Applied Physics. And coming here, we looked for a good place to stay with the family. I am married to Gila. She's a medical doctor in Israel. We have 4 kids now. When we first moved here, we had 3 daughters. And we looked for a place for us to live in, and we found this amazing and nice Chabad community, very welcoming. And now we spent already 3 years here, became part of the community, everybody around. And that's how I got to meet you also, you and your family. So thank you for having us and having me today again.
Of course, it's been a pleasure getting to know you and the family. And just tell us a little bit about also what are you doing next? Because you're leaving now. You're going back to Israel.
Correct. Yeah, after 3 years here in Yale, at Yale University, which is, let's say, the minimum amount that you have to spend usually in these fields. I managed to, Baruch Hashem, get a position in Hebrew University at the Department of Applied Physics at the Hebrew University in Jerusalem. And in Mitzvah Hashem, I'm going to be moving back to Israel in a month and a half and opening my new lab there. You're welcome to visit when you come there.
Thank you. Actually, I've been wanting to visit you here in the lab. I just never got around to it because your research fascinates me. And so I want to talk about that. And also, you're part of the community, but also a very strong, believing religious Jew. So I want to talk about the intersection between religion and physics a little bit as well. But before we get into that, it sounds like your academic background started off in electrical engineering and then veered into physics. So tell us a little bit about how that happened.
Yeah, so it's funny because electrical engineering, I would say, is already on the border between mathematics, physics, computer science. It's in between there. If you have a Venn diagram, so I would say electrical engineering is the cross-section of all the three of them. But then somehow you manage to make another cross-section between electrical engineering and physics and this kind of region called applied physics. But I think everything becomes blurry once you really dive into the details. It's all kind of all the same. You just find your place wherever you can. For example, when I applied for positions, I applied for electrical engineering departments, physics departments, and applied physics departments. So I'm happy where I'm going to. I think it's a great place, and I hope to do well there. But yeah, I started in electrical engineering, and as I moved towards the postdoc and looking forward to my research, I think, my research will focus more on basic science concepts and experiments than what I dealt with in my PhD. So in the PhD, the field, let's say, the interactions and the physics address are similar, but maybe the places and the regions where I apply them and try to learn or use them is slightly different. So during my PhD, I am in the group of Avi Tzadok, Professor Avi Tzadok. He used to be in Bar-Ilan University where I did my PhD, and now he moved to the Technion. So his group focuses on light and sound interactions. It's called optomechanics, the field of optomechanics. And mostly my research focused on optical fibers, which are amazing tools.
They're used now in drones.
That's funny. That's a turnaround in the usage. But the main use is for communication for all our internet. Basically, the backbone of the internet is thousands, millions of kilometers of fibers spread all around the globe and dug under the ocean. And that's how basically we send light from one place to another around the globe. And usually the main purpose of these fibers is to just take the light from one side and bring it to the other and hopefully be as quiet as possible. Just do the job without interfering, without making any noise to the light. And they're very good at that. Somehow people manage to take the same fiber and look at the small miniature changes that they do exert on the fiber and do cause, be it phase fluctuations or scatterings, nonlinear scatterings of light inside the fiber, and use that as a means to learn something about what happens along the fiber path. So that's the field of optical fiber sensors. And there are amazing demonstrations how you can spread a fiber over tens of kilometers and use that as a distributed sensor. So if somebody even drops office clip on the ground and you have a fiber in the ground, right in the ground, you can sense it by the changes it causes, the miniature changes it causes to the phase of light. Because light is so sensitive, you can detect that and identify something happening over there 15 kilometers down the road. This is the field of optical fiber sensors. And
wow.
Yeah, I'm sure it has lots of applications also in the security side, borders crossing and stuff. But it's also used, for example, in pipelines or in oil wells where you have like harsh environments or very long paths and you want to detect signals along the way. And instead of employing, let's say, cameras or personnel to go around the line for tens of kilometers, you just use fiber, which is a dummy, small silica. So the dimensions of it, the optical fiber, the standard single-mode optical fiber, which is the most commonly used one, is a 125 micron diameter silica rod. It's thin almost as a human hair. And to fabricate it or to make it,
manufacture it.
Yeah, and to manufacture it, you pull it down from a tower, like huge tower, and it's cheaper than spaghetti in price per meter. At least that's what we keep telling to people. So it's much cheaper to produce that and employ that as your distributed sensor. And that's amazing. And there are many different physics you can take as your interrogator. What is the mechanism you're looking for? So if you look for Raman scattering or Rayleigh scattering or this scattering or that scattering, and each one gives you a handle on different phenomena. Most of them, let's say all of them, kind of can monitor changes in temperatures, because that's like the basic change. Everything is.
How is it being interpreted? Is it using AI to interpret it, or is there patterns that are well known?
Okay, so in the past few years, there is a very big drift towards AI. Everything drifts towards the AI, but in the basics, it's even before AI. Just you look at the physics, you look at the equations, and you basically solve back what what needed to happen to the light for me to be able to, or for me to detect that signal as the input. And if you carefully design your input and change it accordingly, so you can maybe sweep frequencies of the tunings between your light, or shape your pulse, a very specific pulse that causes or gives you specific spatial resolution along the fiber. So whenever you look at the reflection, you can tell, oh, I got a dip in the reflection after so many microseconds or milliseconds. If I translate that through time of flight to where along the fiber it happened, I can tell what's the exact location.
But then how do you interpret what happened?
Okay, so that depends on your sensor. There are sensors that, and many times your signal is limited, but if you, let's say, implement two different optical fibers with slightly different properties or two different measurement techniques, you can then differentiate between two. Let's say in brilliant scattering, which is mostly what I dealt with, there's usually, you are sensitive to strain and temperature. And there's a figure of merit of how much the resonance frequency changes for each degree of temperature or for each microstrain you have in your fiber. And then how can you tell between the two? You will have to do two experiments, with either two fibers or two different...
You have some baseline.
Also, it's kind of two equations with two unknowns. If you have enough equations, you will be able to resolve both parameters.
So it's not the case that you can drop the paperclip and then know that a paperclip's dropped. You can drop a paperclip and know something's dropped.
Exactly.
Yeah.
Exactly. And then maybe write your drone and send it directly to there to know what...
Right. Yeah, okay.
But I would say, for example, there are people that demonstrated that you can use these optical fibers to listen to people, basically, by eavesdrop. Like it just the talking, us talking produces sound waves and vibrations, and when the fiber vibrates, it also changes the properties of light, the phase of the light propagating inside. So optical fibers in our houses can be used to listen to us talking, basically.
It's amazing. So how did you get from that to the work that you're doing now, that you've been doing for the past 3 years in basically quantum mechanics?
Yeah, okay. So the field of optomechanics, I didn't explain it. Maybe one more sentence about the PhD and then I'll explain. So our mechanism that we dealt with is Brillouin scattering in fibers. And Brillouin scattering is the interaction between light waves and sound waves inside a material. In our case, it was a fiber. We sent light in the fiber, excited mechanical vibrations of the structure itself, and from that learned about the surrounding environment of the fiber. So with a special, we excited a specific kind of acoustic waves, and by that we're able, for example, to measure the acoustic impedance of liquids outside the fiber, where it doesn't even reach. So just by using standard ways or standard techniques for fiber sensing, you couldn't tell that. By exciting these mechanical vibrations that spread outside the core of the fiber towards the outer boundaries, we were able to reach the outer media and measure them. Now, these interactions...
This is all within this tiny...
optical fiber.
Right.
Yeah. Because light, within this tiny 125 micron diameter fiber, there is an even tinier region, 10 microns diameter in the center, which is the core of the fiber. That's where the light is guided.
And how are you measuring this? What kind of tools do you use to measure this?
So the measuring tool is mostly a photodetector, photodiode, where your light basically falls on a material with an energy gap, a semiconductor with energy gap that matches the energy of the light, of the photons, and then the light impinging on the diode generates a photon Hall pair. It takes electron from the valence band and passes it to the conduction band. It's lots of physics here, but you basically generate a photon and hole, and then it generates current in the detector. So you measure the current just by light in the detector, and you look at the spectrum of the current or at the time traces. Now, this was...
So that's already well-established science.
Yeah,
you have to do that.
Yeah. All this photo, it's called electro-optical components. You have laser sources, you have modulators to modulate and shape the light, you have polarization rotators or scramblers, you have all sorts of tools to shape the light and to generate it, to amplify it with amplifiers, because we need to if I want to send signal from America to Israel, I can't just send it on one side and expect it to come on the other. I have to amplify it along the way to be able to detect it.
It loses information as it goes?
Okay,
we'll get to that. Hold on, finish explaining to get how you got into your current research.
The same physics of interaction between light and sound waves can be used not in the field of fiber sensing, but in other fields as well. And one of the fields that it's heavily used in is the field of cavity optomechanics. And in cavity optomechanics, basically, it's not traveling light along the fiber, it's standing waves, standing light waves and standing sound waves in your cavities, in your resonators. And then you can generate this strong interaction between light and sound. And in recent years...
What are the resonators? What are that?
So a resonator is a structure that supports a constructive build-up of light or sound, of field phenomena inside, of excitations inside. So, for example, if I have two mirrors, you can think about it, you know that if I look at the mirrors, I'll see like infinite number of reflections between them, right? But not all light will build up infinite times inside. So we can think of the light as a wave phenomenon. So if you look at the peaks and troughs of the wave, in order for the light to build up resonantively or constructively, you have to make sure that the peak falls on the peak after a full round trip. So like a specific boundary condition on which waves can build up and cannot build up. So you can have the first mode or the second mode and the third mode and the nth mode. So that basically gives you the spectrum of the resonator, like what modes can build up and what waves don't build up. And in these structures that we deal with in cavity optomechanics, we design specifically the resonators, both optical resonators and acoustic resonators, to support a build-up of modes of specific frequencies that we choose to basically boost or to amplify the interaction that we want, that we desire to happen there. And in recent years, in the past 10 years or so, when cooling systems improved the technology...
So 1 second, so just to understand this a little bit better, on my layman's terms, so you're talking about that within light or within sound, there are multiple frequencies, correct?
Sure, the entire spectrum.
Right. So you're talking about choosing or isolating a particular frequency which is going to do what you want it to do so that it doesn't have this infinite reflections or whatever in mirrors, and therefore you can control it.
You usually want it to have the infinite reflections, or you will never have actually infinity, because as light passes, reflections from mirror are not 100%. You have some leakage, some radiation, some transmission, and also along propagation from one side to another, you have some guidance attenuation due to some losses, internal losses in the structure.
But it looks infinite to our eyes.
Yeah, but if you look at the spectrum, it's like a very sharp peak. But usually this sharp peak is not like a delta. It's not like infinitely narrow. You have some finite line width to that, and that has to do with the losses in your structure. The more lossy your structure is, the wider your spectrum becomes usually. And in our case, we try to basically make your resonators as high quality as you can to make it as narrow as you want, and choose these peak frequencies to be exactly what you want, so they generate the interactions that we wish. Now,
what are the interactions that you wish?
I will describe in a second. Just to mention about light, for example, we have a huge spectrum, right?
Yeah.
From ultraviolet to the spectrum is huge. what the light that we see with our eyes is a very narrow band in that visible regime. We mostly use light in the 1550 nanometers, 1.5 microns, which is the light that is used for optical communication fibers. It's IR, it's infrared. You don't see it with your bare eyes. You have to use specific materials to do that. So detectors, for example, are designed for that energy gap, for that frequency. But frequency...
So night vision uses that, for example.
Night vision uses deeper IR, like towards even lower frequencies,
right.
Higher wavelength. So what I wanted to say about the cooling of the resonators is that in recent years, it has been shown that if you cool these resonators enough, you can bring them to the quantum regime, basically, bring them towards their ground state, quantum ground state. And then...
So you're cooling the frequency of light.
You're cooling the structure. You're cooling the structure from room temperature.
And the structure, you're meaning the protons?
No, the resonator itself. Let's say, okay, I didn't describe that before. So you basically take the material you want to work with. In the nano optomechanical community is usually silicon because it's easy to work, but there are so many materials people work with. In our case, now we work with quartz, but you can do that with other materials as well. You shape the substrate, the high quality substrate, because we're dealing with high quality. We want to make sure it's as pure as we can quartz and no some other impurities, or as pure as we can silicon, because that's the material we want, that's the properties we want. And then you shape it with the fabrication techniques in clean rooms. Just like they fabricate all the computers and all the electronics in clean rooms and
make sure that you got no impurities coming in.
Exactly. So the same thing happens now in fabrication techniques for silicon photonics and for other research of material science and chemistry, physics. Everybody uses these clean rooms and fabrication techniques to basically optimize the structures you're dealing with and design them to your needs. So in our case, we take this, let's say, huge chunk of quartz, which is, let's say, 1 millimeter thick. It's huge, 1 millimeter thick.
For you, just to people to understand what you're talking about here, because you're going on the quantum.
Yeah. So let's
say compared to the quantum is huge.
Yeah, compared to quantum, compared to the wavelength of light is 1.5 microns. The wavelength of the sound wave we're dealing with is 1 micron. And
give us an idea of how big is 1 micron compared to this cup.
Okay, so a micron is 10 to the minus 6. It's like the 1 over million. Okay, so in the scale, we have 1 kilo, which is 1,000, mega, million, giga is like billion, tera above that, and keep going, yeah? The other way, from 1, we have milli, which is 10 to the minus 3, or 1 over 1,000, micron, or micro, which is 10 to the minus 6, nano, 10 to the minus 9, so all the nanotechnology, nano thing is all at the region of 10 minus 9. We have, which is 10 to the minus 12. In between, I will just mention, there's also angstrom. Angstrom is 10 to the minus 10, which is usually a scale of the atoms or stuff. So it's usually around 10 to the minus 10, the distance and the lattices of atoms in materials. 10 to the minus 12 is pico, 10 to the minus 15 is femto, and it keeps going.
Right.
But so we deal with a micro. Now, 1.5 microsecond, micrometer, which is 1550 nanometer. That's the wavelength of light that we use. And in that aspect, 1 millimeter is huge. It's like thousands of wavelength. So we take this 1 millimeter thick crystal, high purity crystal, and we shape it into a flat convex shape that basically produces this resonator. So sound waves can bounce back and forth. The wave is basically just a mechanical vibration of the structure. When we speak, we cause mechanical vibrations of air, pressure waves that go. So we produce sound waves, acoustic waves inside this crystal, and they can bounce back and forth. And it has, as I mentioned before, it has specific resonance frequencies, depending on, you have this constructive interference every time you finish a round trip. And it was shown that if you cool down these devices, you can bring this. So at room temperature, it has some population, some thermal population. All these modes, all these resonances. If you just look at any material.
So thermal population, for layman's terms, that means
some heat, some vibrations. Yeah. Mm-hmm. Some energy that produces vibrations. Everything around us at room temperature, it seems to be still, but if you zoom in enough, you'll see everything jiggling around. That's the heat. That's the energy that it has at room temperature. And as you cool down the device or you cool down your structure, you basically take out this energy and freeze all this movement. Now, quantum...
Because the heat is energy, which is causing it to move.
Exactly.
So you're basically, by freezing it, by using cryogenics, right?
Yeah.
You are taking out, moving the energy, so it stops moving.
Exactly. Now, according to the quantum theory, there is always a ground level energy, like some finite energy that you won't be able to take out. Even at zero energy, or zero temperature, there'll still be like a small quanta, the ground state energy level that you still have. Mm-hmm. Like a miniature jiggle or miniature, it also has to do with the miniature level of unconfidence. You cannot know, still, even at the ground state, you cannot tell 100% accurately, like exactly what happens there or where it is. There's still some uncertainty, some movement around.
Okay, interesting.
Now, still, at the ground state...
So is this, in a sense, you're trying to, by using cryogenics, by freezing it, or getting down to however cold you're getting it, you're trying to avoid the collapse of the wave function in some way?
By freezing it out, you're trying to avoid the contamination of whatever information you're going to try and write into a structure to be washed out by thermal population. So thermal population is random. Yeah. It's random. It comes from the environment. You don't really control it. Don't know it. You don't know what you're going to get. It's a random phase, random properties. So if I try to write coherent information that I know, that I control, that I try to put in and read later, the thermal noise around is just going to be noise. It's going to wash out the information eventually. But cooling down the structure and getting rid of all this thermal population, we're basically trying to keep the information coherent as long as we can.
So you're isolating.
Exactly. You're isolating your structure from the environment. You're isolating your information.
So that's the first step, is to make sure it's clean.
Yeah.
Second step is by cooling it down, you're getting rid of that thermal noise.
Yeah. Yeah, but okay, so there are many different ways.
And then what happens? Once you do that, what are you able to detect?
So once you...
Because it sounds like it doesn't work all the way, because there's still that uncertainty.
Yes, but it's a ground state. It's okay. For our purposes, it's fine, because as long as you can tell the difference between zero state and one state, even if zero state still has some uncertainties, but if I can, with high fidelity or with high knowledge, tell the difference between 0 and 1, for example, then I have a kind of an information.
And zero represents what?
The ground state.
Which is that it's what?
That it's completely cooled down, nothing there, nothing, no information no information inside, basically. And the one is one excitation. We're not really used to think about it, but part of the quantum theory is that energy comes in quanta. It's in specific amounts of energy. It's not continuous range of energies. You cannot have all energies that you want. They come in specific small amounts. It's called quanta, basically. That's why it's called quantum. Now, if you have two levels, let's say, maybe you have infinite levels, maybe you have two levels, depends on your physics and what you're dealing with. But let's say I have this resonator and I cool it down all the way to 0 energies. Now, if I'm able to produce or bring enough energy just to bring it to 1. So you can think about it just like a binary bit of 0 and 1. So that's, for example, one simple way to store energy. Yeah, that's not actually the quantum information we're trying to store. That's not even close to that. But still, just differentiating between 0 and 1. this can serve as some kind of a memory. Also, if you produce this one and then make or control the way that it, or bring it down back from 1 to 0 by means of releasing the energy in other way, you can use that as a source. So for example, people use atomic transitions many times, or quantum there are many different physics to implement it. But if you have any transition with energy gap that matches your photon energy, your light energy, you can use that as a single photon source. So not producing light in a continuous wave like we used to think, but like small packets of photons. Each photon with exactly the energy level that we described, these discrete energies that light can have also. So quantized. If I have a transition between an atom with two levels that are exactly in the energy of the photon, and I can excite the electron in the atom from the lower level to the higher level, and then let it drop and generate this energy as a photon, I can use that as a single photon source. And if I can control this transition, bring it up when I want, bring it down when I want, I can use that as my single photon source. And single photon sources are a very important, let's say, tool in the toolkit of quantum experiments, because they all possess many quantum properties, unlike regular standard light waves.
And this sounds very close to some of the things that I've read about in quantum computing, using this type of this 0 and 1s on the quantum level to be able to create quantum computers.
Right.
Is that right?
Correct. It's part of it, yeah.
But before we get there, I want to focus on what I think I'm understanding, because I'm a layman entirely. What I understand about on the quantum level is that it's very difficult, or it's impossible to know whether it's going to show up as a wave or as a particle, correct?
So it's both, basically.
And the second you measure it, that's when all of a sudden it becomes basically whatever you measure it to be.
Correct. Yeah, so that's the concept of the collapse of the wave function.
So it sounds like to me, and just in my layman's mind, is that what you're trying to do here is you're trying to be able to better predict what it's going to be. Is that right? Or am I being too simplistic here?
No, I think you're right in some sense. It's funny because, this concept that when you measure the phenomena, it changes its properties. It's inherent to the quantum theory. So, the moment you try to look at something and measure it, you might even change it from what it was, or it basically affects the state and affects your to use that. So, many, let's say, there's this whole field of research about quantum non-demolishing measurements, QND measurements, which are basically measurements that are meant to preserve the state, somehow be able to measure the state without ruining it. It's hard. Not necessarily, it's not easy to perform, and B, the information you might get is not full also. But it's a complete research topic. In our case, I would say, so for example, for a single photon source, we're trying to use these resonators as means to generate single photons also. But in our case, it's called heralded single photon source. So I can tell you that I have the ability to generate single photon because I detected something else. So there is some correlation between what I'm measuring and the single photon I'm going to generate.
But there still could be an impact of that, because you've measured at something else, that somehow has impacted the outcome that you're looking for. Is that right?
Correct. But if we do it correct, then it's okay, because what I measured tells me I have one photon where I need it, and that would be okay.
But because the outcome is what you want it to be, that it doesn't matter the fact that perhaps your measurement influenced the outcome. Is that right?
I think you're right. I think.
Why do you say?
No, it's also. Yes, I think you're right.
So that itself I find fascinating, because in other words, so when that thing which you're measuring, let's talk about that. What is it that you're measuring, which has an indirect kind of influence, or let's not call it influence, but is able to tell you what the outcome of your experiment is? What is that thing that you're measuring?
Okay, so in our experiment, we still didn't perform it, but
because you can never actually measure the thing itself. It's too small, right?
No, it's not that it's too small, but for example, just how do we tell I have a photon? I measure it, but when I measure it, I take the photon and turn it into electron,
Yeah.
as I described before. So I don't have the photon anymore.
Yeah.
So here, you're a demolishing measurement.
Yeah.
I measured. I have a single photon, but I don't have it anymore.
Yeah.
Right? So I've lost. So for example, in our case, what we do, we use light. I'll describe maybe the procedure, and then maybe it will be clearer. So we take two optical fields, okay, and use the beating between them to generate two optical fields, two light waves, basically generate a mechanical force. It's counterintuitive because we used to think of light as not interacting with the medium around us, just maybe reflecting, transmitted, refracted or whatever, but no, it also can exert forces, mechanical forces. So two light waves generate a mechanical vibration in the crystal.
Yeah.
Then I send the third light wave. With a mechanical vibration, it is scattered to a fourth wave. Okay? So
It is what to a fourth wave?
The mechanical vibration I generated,
Yeah.
together with the third optical wave,
Yeah.
scattered to a fourth wave.
Scattered.
Scattered to a four optical wave. So it's like basically takes the energy and the momentum from the acoustic wave, annihilates it, basically kills it, and takes the third wave into a fourth optical wave in a higher energy, in a higher frequency, and higher momentum. Okay. So that's a process. You generate the acoustic wave, and then you use it. It's like when I described before in the atomic transition. You raise the electron, and when it drops, you get the energy out. For here, it's not like a pure transition that causes the light to come out. I have to come in with a third optical wave at a specific frequency, but I still absorb the energy and momentum from the acoustic wave, kill the acoustic wave, and scatter it to a different wavelength. And then if we do it correctly, if I generated exactly one phonon in this mechanical resonator, then I will get exactly one photon scattered to the fourth wave. So that's the way for us to basically come in with a coherent wave, or let's say like classical wave in the third.
But it doesn't end up being a wave, though.
And then you end up with a single particle, a single photon coming out, single photon source. Now what you measure, so I cannot measure this photon because I won't have it anymore. But maybe
because if you measure, it becomes a wave.
Because if I measure it, it's absorbed by the electrons and in the detector. I'm just saying I want to use this single photon down the road, further down the road.
Yeah. So you don't want to measure it.
I don't want to measure it, but I want to know I have it.
Yeah.
So that's the concept of a heralded source. I want to know I'm going to have this single photon.
So you don't measure it.
But I can't measure it. Yeah? So when I come in with the two optical waves, right, I can detect here a change. Basically, what you do, you come in with the high energy wave, okay? We don't come with two optical waves, we come with one, and you measure a click in the second frequency. I can measure the light wave coming in the second output. And if I measure a single click here, single photon in this wave, I know that the photon here with high energy, a light wave from here, was scattered to a phonon and this wavelength. So I measure this second wave, I know I have one phonon in my oscillator.
But you're calling it a wave, and then you're calling it one.
Okay, I use it, you're right. A single photon centered around the frequency of the second.
And it might not be a wave.
It's a wave packet. So a photon is a wave packet. So
it's a packet.
So
within the wave. So
that's a Fourier relation, Fourier transform. Usually between time and frequency. You can think of it also location momentum. If you know something for sure in one domain, you have zero knowledge in the other domain. So, for example, if I know I'm exactly here, I cannot tell what's my velocity.
Right.
If I know I'm moving
Yeah.
exactly at that velocity, I cannot tell where I am.
This is one of the rules of physics.
Exactly. So the same holds for time and frequency, or time and energy. If I know exactly what the energy, what the frequency of the light, exactly what the wavelength it is, it means it's infinite from minus infinity to infinity in the time domain. So it's the Fourier transform of infinite wave. But if I want to generate a localized wave packet, localized along time, that is basically the single photon, which is like a wave packet that is centered in time somehow, it means that the Fourier transform of that will be also a wave packet in the frequency that contains multiple frequencies and not only one. But that means it's still centered around the carrier, let's say the main frequency of the mode, but it has a finite width. So in this sense, when I say I measure one photon in the second wave, I measure one photon that is centered around the second frequency of waves. So if you build your interaction correct, you can get this heralding. The single click here at around the second frequency tells you have exactly one phonon in your oscillators, exactly one quanta of energy oscillating at a phonon, as a mechanical wave. Phonon is the...
Now, is it possible... So now it's possible what you're saying is that because you've measured that, therefore that's what it looks like, correct? In other words, and that's where it is also.
In other words, if I weren't to measure this single...
Yeah.
So here I think the situation, I wouldn't know, but I'm not sure it would change the reality. So that's something else. That's always the question of what is considered a measurement. What do you need to call something a measurement? Do you need to actually detect it, or do you need it to be detectable, or do you need a consciousness to be like? Yeah. So if I generated this single photon here, even if I didn't actually put the detector there and hear the click, maybe I still... Does it change the reality? That's always the question, right? Would the reality be different? It's a good question. That's part of the mystery of the physics, of the... It's hard to understand and comprehend. And I'm not sure I have a good answer for you here.
Right. But of course, I think that this is what's baffled physicists since the 1920s. But you're dealing with this every single day.
Yes.
And so the question becomes, like, what, at least for the metaphysicist, if you like, for the person who's interested in metaphysics, because I think like the interaction between physics and philosophy leads you to metaphysics. And when I talk to a lot of physicists about this, they refuse to go there. I often get the look, which is, yes, this is something we don't know and we don't understand, but I'm not going to go and speculate on it. It's a bit like the Kabbalists want to talk about the essence of the divine, but they say we can't talk about it, because it's really interesting because they actually use this language where there's the paradox within the divine, within the essence of the divine, that somehow God wanted to create the universe, when it came up in his simple will to create the universe. And then the question is, 1 second, how can God have a will? 1 second, because otherwise he's not pashut, right? It's caused something within the divine, which means that it's subject to change. And if it's subject to change, then it's not God's essence anymore. So now we've got this problem.
Okay.
So there's this paradox, and the Kabbalists say, yes, he can have will and be simple at the same time. How it happens, I don't know. Humans can't understand this. It's not possible to understand. On the one hand, he's simple, nothing can change him, etc. On the other hand, he does have this desire, and how it happens, we don't know. And we're not going to start speculating on it, because it's going to take us to a place which we're scared of, which is more or less the way I am. Because that would limit God in some kind of way. Yeah. So I sense when I talk to physicists about this, that they're like, yes, I don't want to go there because that's going to take me into metaphysics, which I feel uncomfortable with, and therefore I'm not going to talk about it. So in your own practice of physics, as a person who's also a metaphysician in your belief, of course, every day, if you're praying to God, you're davening, then somehow you're also practicing metaphysics. Do you separate these two out? Like, how do you work? How do you figure these two things? In your day-to-day work, when you're dealing with the mysteries of the universe.
Okay, so first of all, In a personal level, I start with separating them, for sure. You have to be a believing Jew in shul, and you have to be the scientist that keep asking questions in the lab, right?
Yes.
But I think that asking questions is also very important in Judaism as well.
But hold on, because I find this really interesting, because when I talk about the universe, right, I think about the classical physical world that we live in.
Yeah.
And when I think about the classical physical world that we live in, it is subject to the classical laws of physics. And they all work within the classical physical world.
Yeah.
The second you get to the quantum level, which is your world of physics, it stops working. And we deal with another whole bunch of phenomena, which a lot of it is paradoxical. Would you agree with what I'm saying?
I'm not sure. We have questions about Shelot Be'emunah also in the classical level of...
I'm not talking about classical. I'm not talking about Shelot and Emunah. I'm talking about, like, although we believe in God, etc., we still believe Bereshit bara Elokim et hashamayim v'et haaretz. There's the heaven and the earth, which God created, and they're the physical. So I don't say, although because this is all a mirage, therefore this doesn't exist. It's solipsism. We don't do that. Okay. We say this is real.
Yeah.
And therefore we're dealing with the physical world, and we do Torah mitzvot in the physical world. We don't say the world doesn't exist because God, and therefore we don't go into that. We still deal with the physical world as it exists. And therefore you might have to deal with the Shelot and Emunah in the physical world as it exists and say, but... And then the Maimunah then is in this different level. It's on a different realm. It's the realm of Emunah, it's metaphysics, and therefore the two are very different realms, and therefore I can separate them out.
Okay.
But when your science is very close to the metaphysics.
Yeah, I see.
So then now your science is different than the scientist who looks at the Torah and says, I've got archaeological evidence to say X, Y, and Z. Your science is much closer to the metaphysical than it is to, I would say.
Interesting. I mean, I heard a few arguments, a few discussions with this. When you start talking about the electron want, so maybe that's where you're going to. But I don't think it's necessarily... I'm not sure it's...
But entanglement, for example.
Yeah.
Is these tell you something about the universe or indicate, or the collapse of the wave function when you measure something. And what you're saying is, even if I'm measuring the thing which indirectly measures the thing, it has an impact on that. When the human mind, you work with it every day, so it's like normal to you, but when those of us who live every day in the classical physical world think about it, it blows our mind.
It blows my mind every time also.
Right.
You never get used to...
Because you're dealing with a paradox.
Yeah.
So when you talk about these things, you say to yourself, 1 second, this is the mysteries. These are mysteries. This tells me in some way that what I see maybe isn't all there is. So that's what you're working every day on that level, which to me is like amazing. Right?
Yes.
But how does that influence then? Because to me, that has to lead me to the next stage. But I see physicists don't want to go there.
So I think... For me, the emunah, the belief, is offer maybe a safety net in that aspect. I think I can say that about many things in life, but also about all this uncertainty, right? Because when you don't have the belief, when you don't have belief in God and in God's will and the shgacha, so you feel like the world is random, and you expect it to be random, and you can be maybe following some logical laws, and then when you hit this quantum regime, it blows up your mind, right? But the moment you have the belief in God, so I find it as a way, like, morid ma'omes. It makes it maybe easier to if that's the way God made the world work, or figure it out to work. Somebody said, if you can think about on the universe like as a simulation, for example.
Yeah.
So we are human beings. We're working at the meter scale. We never experience stuff more than kilometers, maybe. So
yeah.
Or millimeters, micrometers when you deal with hairs. If you zoom in too much or you zoom out too much, it's not like the simulation might be not fully resolved there.
That's interesting because the classical physical world that we live in is very narrow.
Yeah.
the second you try and get out of that, either too small or too big, all bets are off, right?
Yeah. So you have all the relativity effects and gravitational stuff happening at a very large scale. You have the quantum regime going. So
it wasn't designed for us to even discover these things, it seems. Or we were designed to be able to perceive the world in a certain way, which works for us as humans. And all those things were hidden for us for the majority of our existence as humans.
So now the claim is we're not supposed to dig there?
I don't mean supposed to. Let's rephrase it. I don't mean not supposed to, but designed. In other words, it seems like we weren't designed. Humans were designed to perceive the things which are in our field of perception.
So it's this entire discussion.
Design is maybe a bad word. Is also so.
It's like the Matrix, right? When they find out. No, it's the entire conversation about the tolaim in your food. So there is a
creepy crawlies or
because you can. Where do you cross? If you zoom in, everything has bacteria. So where do you draw the line of stuff you're not supposed to eat?
Yeah.
And then some people say whatever you cannot see with your naked eye, it's fine. It's not meant to be asur.
Or else you're eating nothing. You won't eat anything ever.
Yeah.
But.
So maybe that's.
But it seems to me like, in some sense, we're called to also live. When you talk about emunah, like we're called to live on the level of emunah, which is outside of the narrow scope of the classical physical world that we perceive. To me, when I think of emunah, it's like in some sense, we're being called to say there is something beyond the classical physical world that we perceive. And in ancient times, that became, before the scientific revolution, that made the world a very enchanted place.
Yeah.
Because all these spirits around, and etc., which we don't see or perceive, and which we imagine exist, etc. And now, in the age of quantum physics and string theory, if anyone still believes in that, we now have a world where we still have an enchanted world, but in a completely different way.
Correct. It's baffling. On one hand, it seems like we kicked out God from the simple world, but then again, we expected to believe in God not because it explains what we don't understand.
Does God explain, for example, the collapse of the wave function? It doesn't seem to explain it to me.
No,
but it does indicate the mysteries.
Yes. No, I agree. I think that's why I think physicists don't like to go down that, because they're trying to separate.
But why? To me, I ask the question of physicists, because I see it when I talk to physicists. Why don't they like to go there? I even sense you, as a religious person, I sense there's a slight discomfort of you even going there.
Yeah. I feel like it can go both ways. Everything can be used in your favor or against you. The claims go both ways, and I just don't like the direct conflict between the two. I don't like trying to excuse myself. I don't like to try to argue some other people.
Yeah.
So I feel like the best way to live comfortably, just let this be and let that be, and
don't mix the realms.
Don't mix the realms, exactly. But I would say again, in my personal level, I do feel like the fact, like being a believing Jew, gives me comfort and gives me the ability to. Yeah, there are many things I don't understand. That's not the only thing I don't understand. I live in a world that I don't understand, and I accept it. I try to do my best in understanding it. I try to do my best in following God's will, but also in understanding the world, because I think it's part of tzivui. For me, it's like part of understanding the world. It's important. It helps me understand better the world that God made, and B, hopefully using it to do better in the world. Yeah.
So when I started learning about the quantum, it started to become clear to me why the Rambam says that in order to get into metaphysics, you first have to understand physics. I'm not saying this is what the Rambam meant, because I don't think he understood the quantum, because it didn't exist back then. No one thought of it then. It wasn't discovered. But the intuition that the entry point into metaphysics, into the divine, into Vedanta, into knowledge of God, is through the edges of our ability to know and understand things. And then once you get to the point where you say, I can no longer understand, within that mystery is an entry point.
Yeah, okay, but I feel like it's dangerous a little bit.
Why?
Because then you again base your entry point on what you don't understand, about your gaps in understanding.
Yeah, the God of the gaps.
Yeah, exactly. So if now somebody science resolve this mystery, and then suddenly, what do you do with your entry point? Do you have to change your entry point? You have to change your entire concept or understanding.
Right, because what you're saying is that they once upon a time in history they thought that they didn't understand how hurricanes happen, and that was the entry point to the divine. Now we don't understand how the collapse of the wave function happens, and therefore that's the entry point to the divine.
Yeah.
Once we resolve that, now what you're going to do, you're going to say it's going to destroy your faith in God. I hear that argument, but there's always going to be things that you don't understand. In other words, these things can shift.
So it's okay to say, again, for me, I want to believe that. I believe in God because I believe in God. It doesn't have to do with the specific gaps. Yeah.
Yeah.
But when I face a gap,
yeah,
I feel less that tension because I say, okay, I can use God as an excuse for that. So that's why I'm saying it gives me like a comfort. It gives me comfort for this, but I don't want to use that as my entry point for.
Yeah. The only thing, the way I would think about it is slightly differently. Is that in the ancient times, it was a lack of knowledge. I don't know what this is. I'm going to blame it on God. I'm not saying that the collapse of the wave function is God because we don't understand it. That's not the point I'm making. The point I'm making is that it's within the mystery that God is found. Not that God explains things, but it's within the mystery.
Yeah.
It's outside of our realm of ability to understand, outside of our framework.
But, okay, so I think maybe it's true in general, not only in the quantum realm.
Correct.
That within the mystery, it's within the mystery, within the uncertainties, every time we face some uncertainty in life. In general, you face some uncertainties, I'm moving back to Israel. I'm going to open my new lab. I'm so many uncertainties, so many unknowns. It doesn't have to be quantum, but I feel God there. Any uncertainty in your life can lead to a connection with God, and to
understood. But it seems to me that as someone who was data scientist for a while, it seems to me like part of my belief, or part of not just belief, but part of what my contention was that given the data within the classical physical world, we can predict almost anything with degrees of certainty. So in other words, there's lots of things you don't know what might be happening in the future. But if I collected enough data, I could probably predict how your trajectory of your career is going to go with a certain degree of certainty. 80%, 70%. In other words, it's less certainty. The more we're in the classical physical world where we can collect data about things and things happen in a predictable manner, right?
Yes, but you always have this chaos phenomena and all this, butterfly.
So that's the noise. Right. So you're going to have, that's where there's certain uncertainty, but within, you can get more certain about it the more we are in the classical physical world.
Yes, to an extent, Not 100%.
Not 100%.
Still,
no.
I mean, I think we will always have this.
So I'm going to take your point, right? So within that era is where the divine kind of shows up. Yeah. Okay. Even within the classical physical world.
And we always have the human, הגורם האנושי, right? The human part of things, like people acting. You always have the human freedom of choice, right?
Yeah.
So unpredictables, and many people would say, here God can control. We have now, right? Israel just attacked Iran this night. We're expecting to see what the Iranian response is going to be, right? Right? You don't know what's going to happen. Is this their own freedom of choice? Is God going to affect that?
Yeah. So in summary, it seems to me that you're saying that as a person of faith, your day-to-day work in the lab doesn't impact it either positively or negatively, because in some sense you're saying that if I allow it to impact me positively, then it might in the future impact me negatively. Am I right? In other words, so therefore your faith has to be outside of that entirely.
I think the faith should be independent of that.
Independent of that, right.
I think so. Yeah. That's how I feel about it.
It's a different approach to the Rambam, who thinks that it comes through the study of the physical world. Like that knowledge of God.
Yeah, I think I maybe do it the other way.
Yeah.
Again, as I said already a few times, like once
Yeah.
I have my belief, it's easy for me to use these spectacles to look around everything in this context, use that as explanation for stuff.
But there's belief and there's knowledge, right?
Yeah.
So in other words, there's concretizing the belief. So in other words, there's belief, which is, it says the thief, he's sitting at the tunnel and he's breaking into someone's house, tunneling under someone's house, and he calls out, God help me. Yeah. Because his belief, he hasn't concretized it. He hasn't really settled within him in a way that he should actually act in a manner which is ethical or moral, which would be in line with the will of God. So to concretize your belief, it comes this thing of Yidat Hayom, and you should know God. Yeah. And the knowledge of God comes through that, through knowledge. And so that knowledge, so you're saying that the knowledge which you have through science somehow, because you start off with the belief, the knowledge then feeds into that belief?
I think so. Yeah, I feel like the more I know, I understand. It's often marabu masech Hashem. Like the more you learn, the more. But do other people can say it has nothing to do with God?
Yeah.
People say just that's how nature is, and I find it. I don't know. I find it very hard to believe that there is no God, but it's not because of science, just because.
But science reinforces that for you?
Yeah. Yes.
All right. Thank you so much for spending this time with me. Really appreciate it. I've been wanting to do this for a while.
Sure.
Thank you.
Thank you for having me. I hope I didn't say too much nonsense.
From my layman perspective, I wouldn't even be able to judge. Thank you so much.
Okay.